let's keep going with this. All right, so let's keep going with this. All right, so like in the next state, since the input x affects q0 in the next state, in present state q0 affects next state q1, present state q1 does not affect the next state at all. Q1 does affect the next state though, right? So here Q1 is a 0, and you have the option of moving to here or there. Here Q1 is a 1, and you only have the option of moving back to here. And the input x can affect Q0 over here. It can also affect does not seem to affect Q1. But we don't usually think about the individual flip-flop values when we analyze this. We're really thinking of the collection of flip-flop values as the state of the system. So we would typically call this, like state 0, 1, 2, and 3, for example. And so the present state definitely affects what your next state is, right? If your present state is 1, 0, you're guaranteed your next state is 0, 1. If your present state is 1, 1, you're guaranteed your next state is 0, 1. But if your present state is 0, 1, your next state could be 1, 0, or it could be 1, 1. Right? It depends. And so this could be, for example, a traffic light control system where this state corresponds to, you have a yellow light, and depending on the value of an input, you're going to go to either, a green light on west or a green light on south, or something like that, right? So this is how you make systems whose behavior is a function not only of the inputs but of what's happened in the past, basically. And the state bundles together this notion of, what has happened so far. I don't know if that responds to your last comment or not, but if not, let me know. So let's do a simpler looking example. Okay, exactly the same process, but fewer parts and pieces. Okay, but I want you to think of this as that big long process we just did, even if the parts and pieces look simpler. So let's make a JK flip-flop. Let's have one input X. And let's take Q and X and AND them. And feed that to J. And let's take Q bar and feed that to K. And let's just call Q our output. So we only have one flip-flop. This system really has only two states. Q can be a 0 or Q can be a 1. But for a moment, ignore everything we just did. And let's just look at this circuit and think about the kinds of things that happen as this clock ticks. Well, depending on what the values of J and K are, the values of Q and Q bar will change in some way. If J is a 1 and K is a 0, when the clock ticks, this will become a 1, that'll become a 0. That 1 means our output is 1. That 1 gets ANDed with our input, and if our input is 1, we have a 1 coming down here. Otherwise, we have a 0. So we'll have either a 0 or 1 at the J input, and if this output was 1, then this output is a 0, so K is a 0. So this is either 0, 0, or 1, 0 sitting on the inputs, which means the next time the clock ticks, right? If it's a 1, 0, the output will become a 1. If it's a 0, 0, the output will be unchanged, and since it's already a 1, it'll stay a 1. But, you know, if our X input drops to a 0, this will become a 0. Our J input will be 0. And, you know, so there's different things that can happen here. So we want a systematic way to study the behavior of this circuit. So that's the procedure that we just went through. So let's go through it again for this circuit. And I think this is going to be a silly circuit. Well, that doesn't affect the procedure. Alright, so first step, write equations for the inputs and for the output of the state machine. So it looks like J is equal to Q ANDed with X. And it looks like K is equal to Q bar. And Z is equal to Q. Alright, but I'm going to put my state table right down here. So I'm going to list my inputs, my present state, my output, the inputs to my flip-flops, and my next state. Okay, so input X and present state, which I'm just going to call PS, is going to be the value of Q. And I have 4 possibilities. My input could be 0 and my present state could be 0 or 1, or my input could be 1 and my present state could be 0 or 1. So I'm going to list a column for my output Z. And Z is just equal to Q. So it's 0, 1, 0, 1. Okay, next I'm going to list my flip-flop inputs. Well, I only have one flip-flop, but I have 2 inputs, J and K. J is equal to the AND of Q with X. So QX ANDed together, that's 0, 0, 0, 1. So J looks like this. And K is just the complement of Q, so it's the complement of this column. So K is 1, 0, 1, 0. And I'm not thinking about, you know, why any of this is. I'm not trying to make sense out of what this is doing. I'm very programmatically just following a set of steps, right? I wrote down equations for these. I put all combinations of my input variables and my present state, and now I'm just filling in columns for each of these equations that I wrote. And I'm not thinking yet about flip-flops or logic or behaviors or things like that. Okay, but now I'm going to look at my behavior of a JK flip-flop, and I'm going to say, how does the Q output change based on the inputs? And I'm going to make my next state NS, which I'll label Q plus. Okay, if J is 0 and K is 1, Q plus is a 0. If J is 0 and K is 0, Q plus is just Q. And what is Q right here? It's a 1. Right? So this one's worth thinking a little more about. If our input is 0 and our present state is 1, right? That present state 1 means our JK flip-flop is outputting a 1. Because of that and these equations, the J and K inputs will be 0. Well, if you have a JK flip-flop and both inputs are 0, when you clock the tick, nothing happens. The output does not change. So since the output was a 1 before the clock tick, it's still a 1 after. So sometimes filling in this next state is a function of the flip-flop inputs, but sometimes it also depends on the current value of the flip-flop.
How did you come up with the JK values?
These?
Yeah.
From these equations. So J is the AND of Q with X. So 0 and 0, 0 and 1, 1 and 0 are all 0. 1 and 1 is 1. And then K is just Q bar, so 0 bar is 1, 1 bar is 0.
Alright.
So that's basically analyzing this circuit to see what these values will be. All right, if J and K are 0, 1, what's the new value of the flip-flop? It's a 0. And if J and K are 1, 0, what's the new value of the flip-flop? It's a 1. So this is the table we were after: input, present state, output, next state. All these other columns are just intermediate columns to get us there. So this is our state transition table. And we can draw our state diagram from here, and it is a silly circuit, it turns out. So how many states do we have? Well, we have one flip-flop. We have one state variable Q, so that can be a 0 or a 1. So I'm going to draw two states. I'm going to label it 0 and 1. And over here I'm going to put my key, which says I'm labeling the state based on the value of Q. And I have one input, so I'm going to draw an arrow. And on that arrow I'm going to show the value of that input X. Now if I had two inputs, x1, x0, I might label this x1, x0. And then if you saw 1, 0, you'd know x1 was 1, x0 was 0. Okay, just like when we had two state variables, I said I'll label them Q1, Q0. This means Q1 is a 0, Q0 is a 1. Alright, so only one state variable, right? So two possible states. And let's just fill in the arrows. If you're in state 0 and your input's a 0, your next state is a 0. If you're in state 0 and your input is a 1, your next state is also 0. If you're in state 1 and your input is a 0, your next state is 1. Right? And if you're in state 1 and your input is 1, your next state is 1. So really, regardless of your input, if you're in state 0, you're always in state 0. If you're in state 1, you're always in state 1. And our output is equally simple. It looks again like the output is only a function of your current state. So if you're in state 1, your output is 1. If you're in state 0, your output is 0. So I can draw my output in the state, and there's my whole state transition diagram. Let's see, why is the next state for 0j, 0k equal to 1? 0j, 0k, so if your inputs are both 0, the next state is the same as the current state, right? And so down here, my current state is a 1, my inputs are 0, the next state's also going to be a 1. It's going to be the same as this. Alright, that's pretty subtle. So the biggest impediment to understanding these things is actually trying to understand them, okay, too soon. Because there's no pattern we're ever going to find for, like, you know, why in this case, you know, a 0, 0 brought us to a 1, but maybe in some other case a 0, 0 will bring us to a 0, right? Well, it's simply what the flip-flop does. If this had been a 0 over here, then the next state would be a 1. If this had been a 0, 0, the next state would be a 0, because the present state was a 0. So it's really just kind of blindly, you know, writing down the equations, enumerating the possible combinations of state and input, filling in the flip-flop inputs from your equations, and then using the behavior of the flip-flop to fill in what the next states are. And then after you've got that, then you start thinking about it in terms of how does this work for a picture, right? And in this case, we have a machine that whatever state it starts in is always in that state. Input has no effect on it. And the output is always the same as, you know, whatever we happen to call our state. If we're in this state, the output is 0. There, it's a 1. And that's not so surprising because we set this output to be, you know, just coming directly from the Q value of the flip-flop. Alright, now I'm going to change this a little. Suppose our output was the result of an OR, where we had X and we ORed it with Q. So Z is equal to Q or X. So let me get rid of my outputs here. I don't think I've worn down a pencil since I was in like 4th grade, because I don't really use wooden pencils. I use mechanical pencils and I use fountain pens and stuff. But I have a batch of these that I got for a drawing class, and they work nicely on this thinner paper. And I might actually wear this down to a stub, which is cool. It's been like decades literally since I've done that. Alright, so Z is Q ORed with X. So let me change our output column here, Z. And it should be the OR of Q with X. So 0 ORed with 0 is 0, and all of these are going to be a 1. Okay, well, something different has happened now, right? Our output does not just depend on our state. We could be in state 0, and our output might be a 0, or our output might be a 1. Now, if we're in state 1, we know our output's a 1. But in state 0, the output could be different. It could be a 0 or a 1. So we can't just say, you know, if you're in state 0, your output is 0, right? So this is this other type of machine. This is called a Mealy machine. Where the output depends on the input and probably the state. So a Moore machine, right, where the output depends only on the state, we can describe the output inside this circle that corresponds to each state. But with a Mealy machine, the output also depends on the input. So we actually draw the outputs on these transition arrows. So for example, if we're in state 0 and our input is a 0, we know our output is a 1. But if we're in state 0 and our input is a 1, our output should be a 1. So state 0, input of 1, our output is a 1. And if we're in state 1, doesn't matter what the input is, right? Our output's going to be a 1. So we would draw this state diagram for a Mealy machine like this. Okay, and we just interpret it slightly differently. If you're in this state and your input is a 0, then your output is a 1. And on the next clock tick, you'll go back to state 0. Okay, that's a pretty minor nuance, but it pops up in some of the questions, right? So Moore machine, the output depends only on the state. Mealy machine, it depends on the state and also on the input. But here's the practical difference. With a Moore machine, nothing changes until the clock ticks, right? I can be in state 1, 1, right? And if my input happens to be a 1, right, my new state is going to be here and my output's going to be a 1. But that's not going to happen until the clock ticks, right? And whatever the input does not change my output. Okay, my output is only affected by the state. So I can be in a state, I've got a certain output value, that output is completely rock solid stable. Okay, until the next clock tick. But with a Mealy machine, I might be in state 0, and my input is a 0, so my output's a... did I write that wrong? If you're in state 0 and your input's a 0, your output's a 0. right? So I might be in state 0 and my input is a 0 and so my output is a 0. But before the clock ticks, if my input raises to a 1, my output's going to change right away to a 1. Okay, even though the clock hasn't ticked. So the real functional difference is with a Mealy machine, your outputs can change in between clock ticks. With a Moore machine, your outputs will only change potentially when the clock ticks. It's not a big difference though, because we can always turn a Mealy machine into a Moore machine and vice versa. They're equivalent classes of machines. But for analyzing them, it just changes the way we draw our transition diagrams. So Moore machines, we can put the output in the state itself. Mealy machines, we put the outputs on these arrows. All right, so let's try an example from the text. Or possibly from the homework. All right, let's do this question, 6S. Okay, there's a solution in the homework, but we'll do it the way that we've been doing it, and this will probably give you a slightly different pair of approaches. So we have two flip-flops. They're both D flip-flops. Okay, they're labeled D1, D2 instead of D0, D1. That's fine. The outputs are labeled Y1, Y2 instead of Q1, Q2. That's fine. Okay, it's the same thing in the end. Okay, there's no external input to this. Okay, there's no extra thing. In fact, there's just one inverter. That's our whole logic setup. Okay, so there's no outside inputs. There's no outside outputs. There's a system clock which drives both of these clock lines and doesn't really factor into our calculations. Okay. There's also this line labeled CLR apostrophe. This is clear bar. Okay. And it goes into these bubbles next to these inputs labeled R. Okay. So some flip-flops have inputs labeled reset or set. And if you assert those inputs, it forces the flip-flop to a 1 or a 0. And you can make that happen sometimes independent of the clock. Okay. This is useful when you want to put the system in a known state. For example, with our previous circuit, right, we might want to start in state 0, 0 and stay here until the input becomes a 1 and then go to this state. Well, if we start in state 1, 0, we're never going to get to state 0, 0, right? And maybe that's an important state. Maybe that's where some initialization takes place in our factory. So we'd like this state machine to start with its state being 0, 0, which means we would like the state machine to begin with both of its flip-flops being 0, 0. So some flip-flops have a reset input, and by putting a 0 on this line, both of these R lines get asserted and both of these flip-flops will go to 0. So that doesn't usually come into play in analyzing our circuit or drawing our state diagram, okay? But you'll see this used a lot. So what do? We write equations. We don't have to write an output equation, but we have to write equations for the inputs. So I'm just going to write these down and then I'll switch to my camera. So D1 is coming out of an inverter, which is being fed by Y2, okay? So D1 is equal to Y2. I'm just going to call it Q2 to try to stick with like the same notation I've been using. So D1 is Q2 bar, and D2 is what? It's just Q1. Alright, I can ignore my diagram now, and I can start working with equations. So I don't have an input column, I have a present state. And my present state is basically D2, D1. So this could be 0, 0, 0, 1, 1, 0, 1, 1. Sorry, Q2, Q1. It's the outputs of the flip-flops that define your state. Okay, so 2 flip-flops, 4 possible states. Alright, so for each of these I can write down the inputs to the corresponding flip-flops, and they come out of these equations. D2 is whatever Q1 is, so that's 0, 1, 0, 1. D1 is the complement of Q2, so that's 1, 1, 0, 0. And now I can fill in the next state, which is Q2 plus Q1 plus. And again, D flip-flops, easier one to work with because the output is whatever the input is. When the clock ticks, if your D is a 0, the output goes to 0. If your D is a 1, the output goes to a 1. And this is only the case for D flip-flops, right? We can just copy the Q2 column from the D2 column. If D2 is a 0, the new value of the Q output will be 0. If D2 is 1, the new output will be 1. And similarly, if the input of D1 is a 1, then Q1 will be 1. If D1 is a 0, Q1 will be 0. And so this is our present state, next state table. There's no inputs or outputs. We have 4 states. How do you know it's a D flip-flop? Just because it said D1 and D2. It probably should say somewhere, and if you're not sure, you can always ask, right? Are these D flip-flops? And whoever's asking you to do this should give you an answer. But yeah, so I'm just kind of assuming that's what the D is for. Alright, so here's my key. I'm going to label my states according to Q2 and Q1. So here's 0, 0, 0, 1, 1, 0, 1, 1. Again, it doesn't matter how you place these on the page, although sometimes, you know, I got lucky with this one. I didn't have lines crossing each other. If I had put this state, you know, way down here, I might have had a more complex looking drawing. So sometimes you redraw these things after you figure out what they look like. So I just kind of randomly put them down like this. And there's no input, right? It just changes each time the clock ticks. So if you're in state 0, 0, what's your next state? 0, 1. If you're in state 0, 1, what's your next state? 1, 1. If you're in state 1, 0, your next state is 0, 0. And if you're in state 1, 1, your next state is 1, 0. I honestly lucked out with that. So what does the system do? It changes from state 0, 0 to 0, 1 to 1, 1 to 1, 0 and back to 0, 0. Each time the clock ticks, it moves from one state to the next, and it goes through all 4 states in this order. And this is potentially useful because, you know what, if I were to take these 2 Qs and send those to outputs, my output would be 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And we mentioned a while ago, that's what we call a gray code. This is a circuit that will count in this 2-bit reflective gray code. And remember, it's this counting order where only 1 bit changes at a time from one step to the next. So that's a pretty useful circuit. Certainly more useful than this one. All right, but that's the process of analyzing these machines. Now, you know, these get more and more complex. You get to something like this, but it's exactly the same process. Now here we have 2 flip-flops. We already did 2 flip-flop examples. They're JK flip-flops. We did an example with a JK, but the equations are more complex. You have one input X, you have two outputs, and you have to get good at tracing wires. Z1 comes from an AND gate. What is being ANDed? Y1. And where does this wire come from? Looks like Y2. Z2 is an OR gate. One of the inputs to the OR comes from an AND. What's being ANDed? Looks like Y1 naught is being ANDed with Y2. And then that product is being ORed with something over here, which is what? It's the inverse of X. And here we've got a funky inverter where we're using the bubble on the input. So X goes in, X bar goes in, X bar comes out. So this is an inverter. So Z2 is X bar ORed with whatever that product was I said. And you do this for the 4 flip-flop inputs. J1 looks like it just comes from X. K1 comes from this big, long, horrible thing. Right? X bar ANDed with whatever this wire is driven by, which looks like Y2 bar. This is X, and this is coming from Y2. And those get ANDed, the two products get ORed. The result of that is K1. So it's going to be a much more complex analysis, but effectively the same thing. Right? You're going to come up with equations. J1 equals, K2 equals, and so on, and then you're going to fill out the big long state diagram. And when you're following these wires, you want to know where this line is coming from, right? It comes from Y1 bar in this case. If I keep following this, it comes over here. J2 is an input. Okay, there should only be one output connected to any of these lines. And if the lines meet in a T, they're connected. If they cross without a dot, they're not connected. If they cross with a dot, then they are connected. So you have to kind of look at it, right? And so this one comes up with these kind of horrifying equations. Okay, but it's the same process. And these last questions are like even more interesting. Alright, if it's toggle flip-flop, it's exactly the same procedure, except you use the flip-flop table for a T, which basically says if your input is 0, the output doesn't change after the tick. If the input is a 1, the output will flip after a tick. Alright, so this homework got pushed back till Wednesday because I want you to have a chance to work on this in earnest now that we've gone through this procedure, and I want you to be able to ask questions, right? I got office hours tomorrow and such, and then Tuesday after the exam, right, I want to be able to talk about more questions about this so that you can get this done by Wednesday. But it takes practice, right? It's always the same procedure, but there's a lot of steps and there's a lot of places where it can get confusing and it can be unclear what you're trying to do here versus somewhere else. So let me make some comments about the other homework questions, okay? Because there's a few oddities in here. So so question 1, right? If you look at this, right, we've got a circuit. We did this when we first started talking about glitches and timing diagrams, right? The fact that these gates take some time to respond means that, for example, when R changes from 0 to 1, the output won't change immediately from 1 to 0. Okay? R changes from 0 to 1, but Y takes a little while to respond. Okay? So you're thinking about this circuit and trying to do that kind of analysis. Don't try to mimic what happened up here, okay? It's a different circuit, it's going to be a different diagram, but think about how these 1s and 0s flow through this if this is a physical circuit. If changing both of these inputs from being a 1-1 to say a 1-0 happens at some point in time, the output won't drop until a little while later. And if that drop in the output is going to cause this to change its output, that's going to take a little bit of time also. And so, you know, imagine you've got two inputs. Imagine different ways that these inputs can change. They might both start off at 0, and maybe now R becomes a 1. And then maybe S becomes a 1. And then maybe R drops down to a 0. and then maybe R goes back to a 1, and then S drops down to a 0. And yeah, there are unstable situations in here. So yeah, somebody simulated this and found combinations of inputs where the output toggled rapidly. That does happen. Okay, and you'll see that if you work out a timing diagram. You'll see in some cases if the output flips back and forth between 1 and 0. So there's no fixed answer for this one. It's not like you're trying to figure out the number that gives you the answer, right? It's an analysis situation. You want to take the circuit and study it, okay, using this tool that we call a timing diagram. So let S and R change in different ways, whatever ways you think might be interesting, and see what Y does. See how many different behaviors you can get out of this circuit based on what S and R do. And it's got feedback. So S and R might both be 0, and this might not always do the same thing on the output. It might depend how S and R became 0. If there was a 1, 0 and then you dropped S, you might get something different from if it was a 0, 1 and you dropped R. Okay, so spend some time on this one. Play around with it. Look at the timing diagram. I'm still confused, but I kind of get it. Confused about why it was oscillating or about something else. Because again, there's trying to understand why this circuit does a certain thing. Oh, the present and future states. So back to the state table stuff. Let me see. Basically, setting the future state really just depends on the inputs to the flip-flops. And don't think of it as a state. Think of it as what's the next value of flip-flop 1. Okay? The next state is the combination of flip-flop 1's value and flip-flop 0's value. But to compute that, we compute the next value of each flip-flop individually. So we're just looking at what's the current value of flip-flop 1, what's the input to flip-flop 1, and based on those we can tell what's the new value of flip-flop 1. Okay, what's the present value of flip-flop 0, what's the input to flip-flop 0, based on that we can say what's the new value of flip-flop 0. But once we've done that, then we can look at the combination and say, oh, in this situation the next state will be 1, 0, right? Meaning this flip-flop is 1, this flip-flop is 0. But each of these is really a little mini state table, right? Which says if my J and K inputs are this and my current value is Q, then my next value is going to be Q. If J and K are that and my current value is Q, my next value is going to be Q bar. So fill out this table looking at the flip-flops individually, but then when you step back and think about it, look at the states in combination. Okay, cool. Awesome. Yeah, work with that. All right. Question 2, I believe I said to skip. All right, question 3. This is a good one. Input, clock ticks, right? Outputs have gone through all of this combinational logic. Those are feeding the inputs. So when the clock ticks, these outputs change value. As soon as those outputs change value, the inputs to these gates change, right? And so the outputs of these gates can change, and you can have lots of logic here that eventually your inputs to the flip-flops change again. And remember, those changes to the inputs of the flip-flops have no effect until the next clock tick. Okay, so here's an interesting question though, right? What happens if this clock is ticking very, very fast? What happens if this clock ticks and the outputs change because the inputs are getting loaded into the flip-flops, and it starts working its way through this logic? But before all of these gates have had a chance to respond, the clock ticks again. Okay, so it may be that, you know, this gate is very fast, and so this input was set to its proper value, but maybe this takes longer to respond, and so this input has not been set properly yet. So some values could have changed, some might not have. If we do this very, very quickly, chances are nothing is going to have changed. And if we do it, you know, an hour after the last clock tick, everything should be stable and updated. But somewhere in between there, there's a gray zone where some of the logic may have had a chance to calculate its correct values, but some may not, right? We might have an output going directly to one input, and we might have another set of outputs that go through 15 levels of logic before they feed back to a flip-flop input. And if the clock's too fast, those values might not be correct. So if your clock ticks too quickly, your system is going to basically produce incorrect results. Its behavior is not going to be what you saw when you made your state transition table or your diagram. It's malfunctioning, okay? This is the overclocking problem. If your clock goes too fast, the circuitry may not have a chance to respond. So when you set the clock speed for a processor, for example, you're doing it in such a way that whatever the longest path is through all of this and whatever the longest delays are through each of these gates, you're guaranteed things will be stable before the next clock tick. So that's an interesting question. Are there circuits with two clocks? Well, so like your PC has a bunch of clocks inside, right? There's usually a single clock and it gets divided into different things because different systems have different clocking requirements. So your memory subsystem has a clocking requirement. Your CPU has a clocking requirement. But a single state machine with multiple clocks, that would be really interesting. I suspect people have studied that, but I don't know any cases where that's actually used. But it could be kind of cool to have one clock up here and another clock down there with different speeds. There's our friendly recycler outside. Let me close my window. That's so much quieter, right? Can you go over the flow of this flip-flop? Which flip-flop? Okay, so which flip-flop are you asking about? Both flip-flops. So let's see. So this was this, right? We wrote equations which said that D0 comes from an OR gate. It's XORed with Q1, right? Which was this equation. D1 comes from this AND gate, which is Q0 ANDed with Q1 bar. So that's that flip-flop. This truck will leave in a minute, they're pretty fast. And then Z was also the same AND, so Z was also Q0 ANDed with Q1. Okay, and this is a D flip-flop. So we know its new value is going to be whatever the D input is. So, so all the possible combinations of input variable and present state, okay, so there's 8 of those. And we fill in from these equations values for D1, D0, and the output Z, right? So this is just making a truth table from a bunch of equations. Okay, and then the big question is, where does this next state come from? So let's just look at Q1. What's the new value of this D flip-flop after the clock ticks? Well, it only depends on what the D input is. If D is 0, the flip-flop's value will be 0. If D is 1, the flip-flop's value will be 1. So all I have to do is look at the D input for flip-flop 1. And in this case, you know, this input, this present state, the D input will be a 0, because that's what the equation tells us. And so the new value of the flip-flop will be 0. In this case, the D input will be 1, the new value of the flip-flop will be 1. 0, 0, 0, 1, 0, 0. And then we go ahead and we just look at flip-flop 0. So we're just looking at the input to that flip-flop D0, and we're just looking at its output Q0. And our table told us if the input is 0, the new value after the clock tick will be 0. 0, 0. If the input is 1, the new value will be 1, 1, 1, 1, 1, 1. If it was a toggle flip-flop, and the toggle input was a 1, we would look at the current value of the flip-flop, Q1, which is a 1, and we would say, oh, a toggle flip-flop, if the input's 1 and the current value is 1, the new value will be 0. It'll toggle. If it's a JK flip-flop, we would say, well, J is this and K is this, and the current value is that. And a JK flip-flop, if J is this and K is this and the current value is, you know, Q, then the new value is whatever our table tells us. And so we're describing what each flip-flop does after the clock tick. Okay, and then taken together, that gives us the state. Okay, but let's say there are 4 outputs. How then will we be able to deal with figuring out the future state? So what do you mean by outputs? Like extra Z's? Or are you thinking of a circuit with 4 flip-flops? Because just having more outputs has no bearing on your state, right? The outputs are just, you know, output columns that'll be based on your circuitry. But if you had more flip-flops, right, your present state might have 4 values, right? Q3, 2, 1, and 0. And so your equations might contain, you know, Q3, Q2 bar, Q1, and so on. But you'll have 4 next state variables, next state of Q3, Q2, Q1, Q0, and you just calculate each of those based on its corresponding inputs. So your table gets really wide, right? But for D flip-flops, we would have a D3, a D2, a D1, and a D0. And you go from there. What are all of the tables for the different types of flip-flops again? So, like this. So a D flip-flop, the output is just whatever the D input is. A T flip-flop, the output is either stable if T is 0 or it toggles if T is 1. And the JK has a special behavior. It's stable if both are 0. It resets for 0, 1. It sets for 1, 0, and it toggles for 1, 1. And SR is like this, but we can't do the 1, 1 state, so we don't usually worry about SR flip-flops. All right, I will post a practice question just so you can practice with taking pictures and uploading them on Canvas later on tonight. I will put together a short video to talk about timing of state machines, which was our next topic. So, and that deals with this question 3, but it's an important topic. So let me put together a short video about that and post it on Canvas later. And then the rest of this is pretty much along the lines. Question 6 onward is mostly along the lines of what we've been doing. We have to talk about counters and counting modulo something. So question 8 might be a little wonky, but question 9 will be addressed in the video I'm making tonight, and then 10 and 11 are straight analysis. So you should be in fairly good shape to start to tackle most of these questions. I'll post a video later on. I'll put a practice quiz. Catch me in office hours or shoot me an email, and have a good rest of your day. Thanks.
Well, you have a good day.
Thank you. You too.